Thanks very much. Pleasure to be here. My topic is really about hormesis. I don't know if how many of you actually have heard the term before, but we'll go into it in some depth. Just to let you know what my little disclaimers are, for the last 20 years or so, I have received consistent funding from the U.S. Air Force and at a lower level, gifts from ExxonMobil and occasionally from some other federal organizations as well. Okay, so what is hormesis? Well, to introduce the concept, I want you to think about low doses of numerous stressors, things such as exercising, intermittent fasting, hypoxia, heat, cold, ionizing radiation, non-ionizing radiation, electricity, toxins, synthetic chemicals, drugs, phytochemicals, all these things. They can stimulate a wide range of adaptive responses. These induced adaptive responses have the potential to profoundly affect the success of medical interventions for numerous disorders, things like heart attacks, stroke, shock, brain traumatic damage, organ transplants, and surgeries. Stresses that trigger adaptive responses also offer ways to enhance healthy aging, improve human performance, and prevent damage to tissues later exposed to injurious levels of stressors. I believe at the center of this adaptive response concept is the phenomenon of hormesis, a biphasic dose response that mediates processes by which human adaptation and performance can be improved. And as I was listening to the opening session and just kind of reflecting on things in general and kind of wondering what people think of what is health, what is healthy living, thinking of this little rat living in a cage for 2 years in a chronic study, wondering what kind of stresses that little rat has, that mouse has. And how does that rat, is it pre-adapted to, how is it pre-adapted to deal with a heart attack, with a stroke, with brain traumatic injury, with shock? These are things that actually people experience in the course of life's events. None of our studies really seem to address that as an issue of health. How do we adapt to the unexpected? How do you adapt to the death of someone? How do you deal with a divorce? How do you deal with the death of a child? How do you deal with a fall from a bike and essentially a broken pelvis? Actually, you know, those are aspects of life. It's when life is held in the balance. What do our nutritional standards say about that? What do our EPA standards say about that? I bet you they say very little. And what I'm talking about here in terms of adaptive responses is going to say a lot about that. And why isn't that a component of our definition of what is a healthy life and what are we trying to strive for? We're trying to strive for the absence of what? The absence of stress. And I'm here to share with you a view that, in fact, it is actually in the experiencing of low levels of stress that we actually protect ourselves from some of the biggest stresses in life and actually allow us to live a longer life. And that our current procedures that I kind of heard through my 40 years of involvement in the School of Public Health actually doesn't address reality at all. So we'll see if my view of life makes any sense to you. And as I said, we're going to be taking a look at all these things in life that actually stress ourselves and actually can result, in our betterment. So what is hormesis? How can it be used to achieve these public health and medical advances? And how can they be somehow related to your world of nutrition? How can they be somehow related to the broader toxicological regulatory world of an EPA? Well, in my opinion, hormesis really is a dose-response phenomenon. It's characterized by a low-dose stimulation and a high-dose inhibition. It's a non-monotonic, biphasic dose response with specific dose response features. It's not just any kind of biphasic dose response. It really, and I didn't know this until actually I was well into this study, that it really has very specific features. We live in a world of dose-response relationships. We heard it today. We heard about things such as a linear dose-response model, which really drives cancer regulation in this country and the world. We heard of threshold models, which have historically driven non-cancer regulation. We haven't heard too much about the Hormesis model as kind of a new kid on the block. But the hormetic model is, as we see here, the J-shaped dose response. It really is a threshold model. It just happens to have some activity below that threshold. Now, I have about 4 or 5 very substantial Hormesis databases. They have about 80,000 dose responses collectively in them, perhaps a bit more now, all demonstrating examples of Hormesis derived from the published literature, and they have to pass through a fairly rigorous a priori entry and evaluative criteria to get into them. And so, as a result of studying these databases, they have certain characteristics for certain reasons, but what emerges from these databases is that all these dose responses, they have generally similar quantitative features with respect to the amplitude and the range of the stimulatory response. The low-dose stimulation can be directly induced, or it can be the result of a compensatory process following an initial disruption in homeostasis. The interesting thing, at least to me, was regardless of whether this low-dose stimulation occurs by direct stimulation or whether it occurs as an overcompensation to a disruption in homeostasis, the quantitative features of that dose response are the same. And that really struck me as somewhat profound and hard to explain, but how would it be possible? Because there are two fundamental, you might say, mechanisms operating here in a very broad sense, and they both look alike. And the interesting thing, too, is that when you are seeing the generalization of these from plant to microbes to invertebrates to vertebrates at different levels of biological organization, you're seeing the same quantitative features of the dose response independent of the model, independent of the inducing agent, independent of the agent, and the endpoint. Now, how is that possible? How can you have the same dose response features explained by a plethora of different mechanisms in a whole range of biological organisms, induced by different agents, all with different endpoints and showing the same basic features? It sounds pretty basic to me, something that we really need to understand. And what I came to conclude was that the hormetic dose response is actually describing the concept of the limits of plasticity. It's showing how much gain there is in the system. And we only have, as will be shown in the hormetic dose response, a very limited gain of about 30 to 60%. Now, people get into hormetic dose responses and debate that this is let's say, a beneficial effect. Hormetic effect can be beneficial, oftentimes it is, but there are many examples that I can give you in which the low-dose stimulation essentially is not beneficial. Most anti-tumor drugs treated with low doses of anti-tumor agents actually enhance the proliferation of the tumor cells. It's an adverse effect. There are many other examples like that, but there are, an awful lot of beneficial effects too. The only really adverse effect is not understanding the dose response in the low dose zone. You need to understand what's actually going on. Now, in general, there are many thousands of examples, as I've mentioned. Hormesis is, as I've just stated, it's a very general phenomenon. It's independent of model, whether it's a plant, a microbe, vertebrate, and so forth, and all the other aspects that I mentioned before. The key feature is that the amplitude is modest. And that's why it's actually hard to study. If you have a lot of experience in the lab and you have background variability of 10, 15, 20%, it's basically you could delude yourself into thinking you have a hormetic effect when it's just variability. You need lots of doses in that low dose zone. You need to see patterns of inverted U-shaped dose responses. You need to have that observation replicated and replicated again. You have to have a mechanistic understanding behind it. My very first experience with the hormetic dose response was many, many years ago, and my advisor actually made me replicate that experiment with at least 10 times before he was satisfied that the low-dose stimulation and high-dose inhibition was actually a reproducible phenomenon, and to allow me to go forward to the next domain. The stimulatory range can be much more modest, much more variable, rather, but generally speaking, this is really within about 20-fold. You see this, the range is about 20-fold of the no-L or the low-L. You do see stimulatory ranges that can go out over 1,000-fold, and I think that these are real and that they need to be studied as to why this is occurring. Standard hormetic dose response is shown here, in which you have the low-dose stimulation and a high-dose inhibition, everything normalized to a control group. You have the maximum of going up by about 30 to 60%, and then you have the drop-off. You can see the stimulatory range represented there by about a 10 to 20-fold range. Now, hormetic mechanisms, there are many studies that provide mechanisms of hormesis. I was, the biggest challenge that I ever had dealing with the tox community was that I would be presenting them descriptive studies of hormetic relationships, hundreds and thousands of examples, and I was told by the editor at the time of Tox Sciences that toxicology worships at the altar of mechanism. And until you can come up with mechanisms of hormesis, you will not get into our journals. And so, you know, sent back to, to my room by the teacher, so to speak. I'd have to say that in 2013, we published a paper in Critical Reviews in Toxicology identifying the specific mechanism down to the level of receptor and cell signaling pathway for 400 distinct different hormetic mechanisms. We now have an additional 600 that is now being submitted soon to another journal on that. I believe we have more mechanistic understanding because of the demands placed on us than any other mechanism, any other dose response model has been required essentially to show, because we had to prove our stuff more than the others actually had to. And so basically, and the interesting thing, regardless of mechanism, regardless of pathway, regardless of receptor, the dose response features really are the same. It's really an interesting idea. Okay. Now, so I mentioned all these different things here. Now, hormetic responses, they're integrated responses across multiple levels of biological organization. You see this in cell proliferation, you see them with fecundity, you see them in tissue repair, you see them in behavior, learning, disease resistance, DNA damage, tumor incidence, aging, and longevity. Actually, anything that's important to you in your life will have a component of a hormetic dose response associated with it. I'm going to show you some examples now. And I chose these just to show you a wide range and diversity, not to try to tailor them to a nutritional crowd or a toxicology crowd, but to more or less illustrate the generalizability of it. Here you have an example of the effects of ethanol, acute ethanol, on overall social activity in adolescent rats tested on day 30. You have the high-dose inhibition of the activity, but a flip over the control group, and you have the low-dose stimulation going out by about 50%. I've actually visited the lab where this was taking place, saw the animals, saw them on tape. It's actually a very reproducible phenomenon. Here we have fruit flies and methanol. Methanol, very high doses, is harmful to the longevity, but at low doses for males and females, you have a flip over to an enhancement. It's a very reproducible assay in many different laboratories. You have, in the next one, sodium arsenate, taking a look at how it affects essentially lymphocyte proliferation in these bovine lymphocytes. High doses, it's very inhibitory. You have the low-dose stimulatory response. Here you have, I chose this one deliberately because this is methyl mercury. one of the most toxic neurotoxins that we know and very fearful of. Now, you would think that methylmercury is like, there's no potential safe level or beneficial response to methylmercury. And in this neuronal cell line, you can see that in fact at high doses it's very toxic, but at low doses there is a consistent increase in the vitality of these neuronal cells. I see the same thing actually for other neurotoxins as well. Here I'm showing you an example of morphine and its effect on the induction of seizures. Now, what you have is a model system that induces seizures, and if the chemical that you're testing essentially increases here, as you can see it, it means that it's making it more difficult to induce the seizure. This would identify morphine as a potential therapeutic agent. I looked at this, not being an expert at all on seizures, and I said, that's Hormesis. And I went on to find about 70 other anti-seizure drugs, essentially everyone that I could find in preclinical studies. They actually had a biphasic dose response. Same thing was true for anxiolytic drugs, things which reduce anxiety in individuals. Tested in rodent models, they really try to see to what extent they can get the rodents to spend more time out of the dark area into a lighted area, because they don't really want to go into a lighted area. It'd be like me driving down to New York City, something I would never do. What's going to make me do that? I don't know. But drugs can get the rodent to spend more time in the lighted area, interpreted by the psychology researchers as reducing their anxiety. It's an inverted U-shaped dose response consistent with a hormetic response. I found essentially the entire literature of the anxiolytic drugs in the preclinical studies always showing these types of inverted U-shaped dose responses. We're published widely on that. Here's an example of resveratrol, looking at its cardioprotective effects. Now here you have a J-shaped curve in which at low doses it is reducing the myocardial infarct damage. At high doses it actually makes it worse. Now the concept of preconditioning that I started the slides off with, I've got a couple of examples for you here, but just as a little bit of a little twist on this, even though preconditioning's been around since about 1928 when somebody found that low doses of radiation could protect against a subsequent dose of radiation in plant models, it really just exploded on the world in 1986 when researchers at Duke, using a relatively low hypoxic stress to essentially a dog model, were able to protect the dog against a subsequent massive myocardial infarction caused by major ischemic reperfusion stress. And they reduced the damage by about 70%. I mean, it was profoundly significant. So that a low stress prior to the big stress was really protective. Then it was reproduced, and it was generalized to the brain, to the kidney, to the liver, to the lungs, to the skin. This idea that you could pre-challenge an organism with a low dose of a stressor, and it could be very useful, very protective. And then somebody had the ingenious to see that you could actually take that low stress and do it after the major stress and get equal protection, and they call that post-conditioning. Well, the interesting thing was when you look at this vast literature now on preconditioning and post-conditioning, and you identify studies that have looked at lots of conditioning doses, what do you find? Well, you actually find that it's invariably an inverted U or J-shaped dose response. I just had 2 papers just got accepted in pharmacological research. They're online now, trying to make the case that preconditioning is hormesis. This is showing you here an example of oxidative preconditioning for 24 hours with H2O2 over a range, and then on these mouse neural progenitor cells. And then basically, you then give them a big dose of H2O2 later, and you can see that in fact, that the damage is decreased from the big dose if you pre-dose them with the low dose of H2O2. This is another example here, using nitrite prior to a major myocardial infarction. You get a significant decrease in the infarct damage. This is being used very widely now in terms of trying to pre-stress stem cells before you inject them into damaged heart tissue, because the unstressed stem cell doesn't do very well in a very compromised environment. The preconditioned one does. If you take skin that has to be essentially essentially for some sort of skin burn victim, and you're moving it from one part of the body to the other, preconditioned skin takes better than the other. Now, example of hormesis and cancer. It's a study here, a very large study at Oak Ridge, looking at about 500 to 750 mice per square or dot that were given essentially gamma rays. And you can see that at low doses of these gamma rays, you have a decrease by about 20 or 30% of the lung adenomas, but at high doses, it begins to increase. And if the linear model was really right, you would expect that this relationship would just be linear right down to the 100%, but it goes below the curve, and it's consistently below the curve, and it's a very large study. It's not the only one. There are many others like this. There's a Japanese study I'm trying to show you here, in which they're looking at an exposure to essentially constant exposure to 0.65 milligray per hour, which is about 50 times above background exposure. And they're comparing it to the non-irradiated group, and these were now exposed for 90 weeks. Now, I just want you to show that the red one over here is actually the group that got the radiation its whole life. And they're outliving the controls essentially at the 90-week mark. 70% of the radiated ones are alive, and 40% of the controls. When you look at the animals, representative animals at 90 weeks, this is what the control group looks like, and that's what the irradiated group. I'd have to say that the control group looks like my dad did at 95 when he died. I mean, he lived a nice long life. He was healthy pretty much up until the end in a way, but he was well worn. This mouse over here had smooth skin. It was plump and healthy. I said, give me some of that. Now, over here, in terms of the dose-response relationship, Herman Muller gets a Nobel Prize in 1946 for his work in 1927, showing that radiation could induce mutation in the gonads of a fruit fly. If Dr. Muller had just lowered the dose a little bit, and he would have actually got the dose response right, and they might have given him 2 Nobel Prizes instead of 1. Now, the next thing is taking radiation one step further, but the cancer process a little bit further down the line, taking a look at neoplastic transformation. High doses, again, enhance the damage, but low doses actually cause the J-shaped curve. Over here, DDT, banned as a carcinogen, having other issues as well, but when the Japanese people, researchers evaluated this in a very detailed study using liver foci as a model, high doses got exactly what was predicted by the NTP bioassay, but low doses actually consistent decrease, showing a decreased risk, a hormetic dose response. They spent considerable time on the mechanism, could explain very well why it was harmful and why it was protective. In the mega mouse study, looking at, we had 24,000 animals that was done at NCTR, looking at the bladder cancer endpoint, which is one of the standard endpoints that they looked at. A group of 14 SOT experts reviewed all their data and essentially demonstrated with their data a J-shaped dose response, a clear carcinogen at high doses, and clear hormetic respect at low doses. They did have these findings in 6 different rooms, all with J-shaped dose responses. So hormesis has many applications in drug development, anxiolytic drugs, anti-seizure drugs, memory-enhancing drugs, osteoporotic drugs, wound healing preparations, all showing hormetic dose responses. You have numerous pre- and post-conditioning studies display hormetic dose responses as well. You have hormesis can fit in and account for certain types of chemical synergies that we can talk about in the question and answer period. So what is Hormesis indicating? In my opinion, this low-dose stimulation is different than high-dose toxicology. To measure biological performance, not toxicity, it determines how much a system can respond. So Hormesis is the first quantitative estimate of biological plasticity. Essentially, the hormetic stimulatory response is constrained by the limits of plasticity. And some takeaways for you. Hormesis is a general and central biological concept. It affects all disciplines utilizing the dose response. It represents a general adaptive strategy through which biological performance is enhanced and mediated. It provides the theoretical basis and molecular foundations to create biological shields to protect against chemical, radiological, and microbiological threats. And I would contend, as I did in the beginning, that creating biological shields to protect yourself against all kinds of adversities has to be added to the definition of health and how we are going to live. I mean, you just don't live at a constant temperature in a little cage like a mouse or rat does. You have all kinds of bumps and bruises that affect your life. You have to be able to survive those bumps and bruises. Induction of adaptive responses, building the biological shield is part of it. This has implications for numerous and diverse medical interventions, as well as affecting health and performance of military personnel, athletes, and the general public. Failure to consider the hormetic dose response within hazard assessment and risk assessment, in my opinion, is a serious failing of modern risk assessment. Risk assessment needs to consider the entire dose response continuum in order to serve the public health. Thank you very much.